Surprise! The return of Bernoulli numbers. I guess you guys know about the Bernoulli numbers, right? These are the numbers that help us like sum up the kth power of natural numbers, right? If you do not know about it, let me just quickly give a short introduction. So let's say if you want a sum of 1 to the power k plus 2 to the power k plus 3 to the power k up to n minus 1 to the power k, right, for some k. Then this sum, which is denoted by as subscript k up to n minus 1, is actually given by 1 by k plus 1 sum from m equals to 0 to k, k plus 1 sub m b sub m n to the power k plus 1 minus 1. Okay, and to make this formula true, we actually define the Bernoulli numbers, right? And actually, like Bernoulli numbers, okay, there are also like two sets of Bernoulli numbers denoted by b superscript minus or b superscript plus. And actually, to make this formula true, the set of Bernoulli numbers that we need are like 1 and then minus half and like 1 over sixth and then 0 and then 1 over minus 1 over 30 and then 0 and then 1 over 42 and then 0. So for all, like except for 1, it's all 0, right? And minus 1 over 30. So these are the Bernoulli numbers that help this make this formula true, right? But for today's discussion, we are gonna change this value of b sub 1, right? So we are gonna use the other system of Bernoulli numbers, and because you will know the reason later on, okay? So yeah, these are the like Bernoulli numbers, right? And we already know them for like non-negative integers, right? So we don't really I mean most of the time like people don't really know the Bernoulli numbers with subscript negative numbers or fractions, you know. So this generalization would be the topic of today's video, and I definitely believe it's interesting for a lot of you guys, right? Okay, okay. So first of all, before I go to Bernoulli numbers, maybe I can show you some connection between Bernoulli thing and then the zeta function, right? I guess you guys know that zeta of k is 1 by 1 to the power k plus 1 by 2 to the power k plus 1 by 3 to the power k and up to so on, right? So let's say if we are trying to find zeta of negative k, this just becomes 1 to the power k plus 2 to the power k plus 3 to the power k and so on. Notice, right? We might have noticed that this is also just this as k n minus 1 sum where n goes to infinity, right? So from there, you might feel a little bit of connection between zeta and Bernoulli thing, right? But yeah, let me show you the exact relation between Bernoulli numbers and zeta function, right? Okay, so there's this formula. Yeah, it says Bernoulli. Okay, if you want to extend Bernoulli numbers, negative numbers, right? What you can use this formula. This is the like analytic continuation of Bernoulli numbers minus n s times zeta of 1 minus s. And similarly, if you replace like s minus, if you basically replace 1 s minus 1 with n, you get another formula for zeta, right? Which is zeta of minus n is equals to negative b subscript n plus 1 by n plus 1. So these are basically used when this negative n, I mean, to find, let's say, zeta values for negative indices, or this also for when negative indices, you know, to extend them. So let's try to export those values today, right? And then yeah, and then that's the goal of the video, right? We wanted to export these values and also explore new things. So yeah, okay, before we go there, we already know these Bernoulli numbers, right? These known Bernoulli numbers. Let me also talk about the known zeta values, and then we are good to go. Let me also talk about the known zeta values. So we already know that zeta of 1 is infinity, zeta of 2 is pi square by 6, zeta of 3 is just zeta of 3, zeta of 4 is pi to the power 4 by 90, zeta of 5 is just zeta of 5, zeta of 6 is pi to the power 6 by 945, zeta of 7 is just zeta of 7, zeta of 8 is pi to the power 8 by 9450, and so on, right? Okay, now based on this, let's try to find this Bernoulli number with negative subscript and zeta, also zeta, right? With also, yeah, we will get to prove the things like zeta of -1 is -1/12. You might have heard this, right? Also, like maybe you have heard of this, yeah. So basically, this actually means that sum of all. I mean, this doesn't mean, but you can like compare like this as sum of all natural numbers. You can compare this as just sum of one, right? That's pretty interesting. Okay, so yeah, so that's just analytic continuous. You cannot really compare, but people do make those jokes. Okay, uh, so Bernoulli number with subscript -1 will be just 1 times zeta of 2. That's pi square by 6, right? So that's what I told you earlier over here. Similarly, for -2, this will just be 2 times zeta of 3, but zeta of 3 is unknown, so that's it. For -3, this will be 3 times zeta of 4. Zeta of 4 is pi to the power 4 by 90, so this is pi to the power 4 by 13. So this is how you can also find all other Bernoulli numbers with different subscript, right? Yeah, like this will just be 4 times zeta of 5. Similarly, let's say if you want to find Bernoulli with subscript half, this will just be half times zeta of 3 by 2, right? And maybe zeta of 3 by 2 is known. I don't really know about that. And you can also, if you want to find the Bernoulli with half, that will be negative half zeta of half, right? So yeah, so this basically helps us define Bernoulli numbers for all these indices, right? Similarly, for in the zeta function, like if you want to, let's say, find zeta of let's say 0, right? That will just be minus Bernoulli number 1 by 1, and Bernoulli number 1 we have. Yeah, so okay, see, now that's where like our assumption becomes helpful, because we define it as half. This will be minus half, just like expect what is expected. Similarly, zeta of -1 is now negative times b2 by 2, and b2 is 1 over 6, so -1/12, right? Exactly this formula, this well-known thing. And zeta of -2 is negative b3 over 3, right? And b3 is 0, so that's 0. So that's why actually, because this odd Bernoulli numbers are 0, all these are also 0, right? Except I mean, n should be natural number, okay, not 0, okay. So yeah, you can actually see that. And now for -3, this is just negative b4 by 4, and b4 is -1/30, so this is 1/120, right? So you can actually get all these zeta values as well using the Bernoulli number. So that's a pretty deep connection, right? Yeah, and that's what helps us find all these Bernoulli numbers that could extend them also all the zeta values, right? And there's actually even a more deeper extension of Bernoulli numbers. Okay, so basically all these Bernoulli numbers are just Bernoulli numbers of 1. I mean, there's also this function Bernoulli. For every Bernoulli number, you can also give an input x. So there's also this Bernoulli function, right? And these Bernoulli numbers are just this Bernoulli function at value 1. For general value x, this is actually defined as um okay, let me show you how it's defined. So Bernoulli number subscript n plus 1 x is defined as negative n plus 1 zeta of minus n comma x, right? Yeah, and like if subscript and if you put x as 1, this Harvard zeta, this is actually Harvard zeta function. Basically this means, let's say if I have s and k, this means sum from n equals to 0 to infinity 1 by n plus k to the power s. So this is what it means, right? And if k is 1, this Harvard zeta function just becomes normal zeta function. So yeah, when x is 1, so this becomes normal Bernoulli thing. But otherwise, this is even a more general. Every Bernoulli number, it's sum with some function x. So this is called Bernoulli function. So there are actually a lot of generalizations of this Bernoulli thing, and then all of those are quite interesting. I tried to share you one of those today, and I definitely hope you enjoyed it, right? So that was it, guys. So definitely we found out some interesting Bernoulli numbers in this video, and also some like interesting zeta values. I hope you enjoyed them. Thanks for watching. Do share with your friends, and I look forward to seeing you in the upcoming video too.